Dear students, welcome to my YouTube channel PCM Academy. We are discussing quantum mechanics course, and we have discussed a lot of things about quantum mechanics from the very basic point, that is from photoelectric effect. We are actually discussing on quantum mechanics, and we will reach to the advanced level also, that is first we will cover the syllabus of IIT JAM, then we will cover the syllabus of JEST, neet also. Okay, so from the very basic point of quantum mechanics we will reach to the very advanced point of quantum mechanics, and all the theory part I will be covered here, and some solved example also will be covered in this course. So if you are new in this channel, then please subscribe my channel and hit the bell icon also, so that you will get the new notifications as I will be uploading many videos on your course. Okay, and various types of course already uploaded in this channel. If you see the playlist, you can see the course on mathematical physics, and that is basically the JAM syllabus is completed, but for JEST or neet syllabus I will be uploading very soon. And otherwise mathematical physics I have already uploaded some videos on electricity and magnetism, that is electromagnetic theory. That is also not completed now. It is basic electrostatics course was uploaded, but very soon we will be uploaded more and more videos on these topics, these advanced topics also, that is magnetism and electromagnetic theory also. Okay, so first let me finish this quantum mechanics, then we will return back to the electromagnetic theory also, then I will discuss all the topics, okay, that you have in your syllabus, all the topics, modern physics and atomic nucleus. Okay, so every topics I will be discussing over here with some solved examples, but you have to practice lot of questions from your own. Okay, you will be benefited if you solve questions more and more. Okay, and basically I suggest you first to solve the questions of previous year exam. So if you are aspirant of JAM, then obviously you have to solve the JAM questions along with this JEST question, along with this GATE question. You have to solve these kinds of questions. So previous year question is very important, and if you solve these questions, you will get some idea about the question pattern and the level of question. Okay, so that you can develop yourself according. Okay, and you will be obviously you will score a very good marks. Okay, so let us discuss about this particle versus wave. Today I will discuss about particle versus wave. In the last class I have discussed about the de Broglie wave and the Davison-Garmer experiment. That was the first experiment that proves that the particle have wave nature, and the particle selected for that experiment is electron. Okay, and I have told you earlier that the wave nature of particle actually wave for any kinds of particles, if a particle is moving with some velocity, then corresponding to that particle there is a wave, there is a wavelength, and that is actually the wave particle duality according to de Broglie. Okay, but the question is that what about the macroscopic particle? So I have calculated some little calculation about the last class, that for macroscopic particle, something like a sand particle, or very actually if you talk about the 1 gram or 1 kilogram mass, so the macroscopic point of view, this 1 gram is also very large mass, because in microscopic view, if you talk about the microscopic point of view, then you know the microscopic particle, something like electron, have very low mass, that is 10 to the minus 31 kg, you know, and with respect to that, if you talk about a sand particle, then that is very high mass. Okay, so the wavelength of microscopic particle, and if you talk about the wavelength of macroscopic particle, so what is the difference between these two? So we have calculated earlier, if there is a microscopic particle, that is for electron, if you talk about electron, then we have seen that the de Broglie wavelength corresponding to the electron is of the order of 10 to the power minus 9 angstrom. Okay, but if you talk about the particle, something like a sand particle, which have mass 1 gram, and the corresponding wavelength is of the order of 10 to the power minus 34 meter, something like this. So you can see this wavelength is very low. This is not perceptible actually, this is not predictable, but this wavelength is predictable. So there is a wavelength corresponding to a microscopic particle as well as for the macroscopic particle, but the wavelength is perceptible only if the wavelength is actually comparable to the size of this particle. So you can see here this is comparable to the size of this particle, but this is not this is very too much different, that is 10 to the minus 34 meter. The size of the sand particle is not too little, this is here 10 to the minus 34 meter. So you can conclude that if the size of the if the wavelength is for a corresponding particle, if the wavelength is size of that particle is comparable to the size of that particle, that wavelength is perceptible, otherwise it is not perceptible. But there is a wavelength. If a particle is moving with certain velocity, maybe it is a microscopic particle or it is a macroscopic particle, but there is wavelength, but this wavelength is significant or not, that is the question. Okay. So always whenever we talk about the quantum mechanics, we are talking about the microscopic particle. Okay. So we will always talk about this kinds of electron, proton, neutron, these kinds of particles, this kind of microscopic particles. Okay, so basically most of the cases we will talk about the electron. So, and now if you see classically that what is the difference between the particle and wave, and if you see quantum mechanically that what is the difference between particle and wave, then you will be surprised. Okay, because in classical physics this particle and wave are completely exclusive property. So there is in classical physics, you know, there is some property of particle and there is some property of wave. So that property, the which properties are properties of particle, wave do not show this kinds of behavior, and the property which wave show can't show the particle. Something like if you talk about some phenomena, if I give you some examples, suppose that if you talk about some phenomena, something like if you talk about diffraction, if you talk about interference, then these kinds of phenomena in classical physics can't show particle. But if you talk about collision, this is actually the collision. If you talk about collision, then this is the property of particle in classical physics. In macroscopic world, if you talk about in macroscopic world, then the particle have the property, the particle show some phenomena that is called collision, you know, and if you talk about the wave, they show diffraction and interference, this kinds of thing. And another thing also, if you talk about the particle and any any physical attributes of the particles, any physical attribute, the first attempt, if you talk about the dynamics, you know, in dynamics you have to, if you want to study motion of a particle, dynamics of particle, then first you have to see the location of the particle, that is the position vector. So the physical attribute that you need to describe the motion of a particle is first is the position vector, which may be the function of time or function of space also. And obviously in quantum mechanics, or you can say for wave property, so let me first don't take the word quantum mechanics. First we like to see the particle and behavior of particle and wave in classical. So in classical physics, what is happening in classical physics, let me talk about this first. So in classical physics, we treat this particle and wave completely to mutually exclusive thing, and a particle can be described by a position vector r of t, and other physical attributes, something like velocity, acceleration, can be derived from it. If you talk about the velocity, then it is dr by dt. If you talk about acceleration, then d2 or dt. But a wave is represented by a wave function psi, and that is in the form of a to the power I k dot r minus omega t. And you know, this is actually the phase angle, or you can say the phase constant, k dot r minus omega t is actually phase. And this phase is obviously, it is a you can see that this is a function of space and time, and if the source is coherent source, the wave source is coherent source, then there only the time is, in that case the phase is the only function of position or only function of space, not the function of time, if the sources of wave are the coherent source. Okay, so that I will be discussing in optics in details. So here this is the phase angle actually, and we have to first define the state of the wave, you can say. So the physical attribute, that the information that you can get about a wave. So if you study the wave motion or something like this, you need to define the wave function first in this way, But for study of a particle, particle dynamics, we have to write first the position of this particle, and then we can derive the another physical attribute from there. Okay. So classically this is the mutually exclusive thing. And if you take an experiment, so the double slit experiment for particle as well as for wave in classical physics, then you can see the following. So let me take a double slit experiment, then you can understand in depth that what I am going to tell you about, or what I want to tell you about the particle versus wave. So what is the behavior of particle, what is the behavior of waves in classical physics, and what is the behavior of particle and wave in quantum physics. So first let me perform the experiment in classical region, that is in macroscopic world. Okay. So in macroscopic world, let me take about the talk about the double slit experiment. Double slit experiment. Okay. Now in double slit experiment, so we have two sources. So this is our source S1, S2. So from this is one source, and from here, so we have a two source S1 and S2. So this is the main source. Then here is S1, S2, and here a screen. Screen is over here. Okay. So now we will see the intensity pattern here. So let me take from here. Suppose a bullet are actually firing from here. So a number of bullets are firing from here. So some bullets will be passing through the slit of S1, and some bullets will be passing from the slit S2, and they will gather on the screen. And the intensity is nothing but the number of bullet reaching here per unit time, per unit area. So now first, if you switch off this slit S2, and if you only allow the bullets to pass through this slit S1, then you see the intensity pattern over here, something like this. And suppose this intensity is I1. Now if you perform the same experiment again, and now if you close this S1 and if you allow the bullets to pass through this slit S2, then what will be happening? So in that case, so this is the screen now, and this is S1, S2. Now let us close this S1, then you can see the intensity pattern of bullets on the screen is just something like this. So this is I2. Now if you open both the slit, then what will happen? Then you can see the intensity pattern. So let me redraw here. Okay. So if you open this slit S1 and S2 also together, then you will see the intensity pattern something like this. So if you see, then this intensity will be nothing but the summation of these two intensity, that is I1 plus I2, and that is obvious for the particle in classical physics. But if you take a source of light here, something like wave source, okay, then what will happening? In classical physics, you can see whenever if you allow to pass this light from this slit S1, you will get this intensity pattern, same intensity pattern you will get, and if you open the slit S2, you will get this intensity pattern also. But if you open both, then you will get interference pattern, that is something like different. This is not I1, I2, I1 plus I2. So here will be the maximum, then other side there will be minimum, something like this. And this intensity, this total intensity is not I1 plus I2. This is actually I1 plus I2 plus 2 I1 I2 into cos delta, to root I1 I2 into cos delta. So this intensity is depend not only I1 I2 but also the phase difference between this S1 and S2. And for this coherent source, I told earlier that this phase difference will be only function of space, not the function of time. Okay. So that is with respect to time, this phase difference is constant. So this will be the unit intensity pattern. So you can see this is the classical view of some bullet, and if you talk about wave. But now if you see the quantum view of this experiment, then you have to take a microscopic particle, that is electron. So now if you talk about the quantum view of this particle and wave, so let us talk about now quantum view. So in that case, so instead of bullet, now these are electron. Now if you allow to pass this electron from this slit S1, so it will show something like this. And if you allow to pass this electron here, it will be showing same this I2. And now if you open this to both, then you can see this intensity pattern. There is the interference. So you can see electron is a particle, but this particle show its behavior like wave. You can see. So actually, if this will be showing the particle behavior, then the intensity will be just I1 plus I2. But you can see this intensity would be for electron also I1 plus I2 plus 2 root over I1 I2 cos delta, that is something like wave. But the interesting thing is that if you open these two slits for electrons, and if you illuminate one of this slit by light, if you want to see by using light the interaction of electron, so if you want to illuminate one of this source, then you can see immediately this interference pattern will disappear. So please understand this point. First, what is happening over here, if you open the two slit for electron, it will exhibit the interference pattern something like this. But if you want to illuminate one of the source, either S1 or S2 or 2, if you want to illuminate this source S1 or S2 by light, so you cannot see this interference pattern. This is because of the fact that the electrons, whenever the electrons are interacting with the light, whenever you give a light to this source S1 or S2, the electrons will be interacting with the light, and immediately the behavior of electron will be changed. So you cannot interact with the electron. If you want to see its actual behavior, you cannot see by using illuminating of light or something like this, any electromagnetic wave, any radiation. So whenever you put radiation to this electron will interact with this radiation, and in that case it will simply behave as particle. So this is actually the microscopic behavior of electron that we cannot detect by our human eye, or we cannot interact that electrons on that state when the electron is behaving something like its microscopic behavior, its wave behavior. If you want to interact with this electron at that point, then it will change its behavior. So this is actually the unpredictable thing. You cannot predict this, you cannot see this, you cannot interact with the electron. If you want to interact, then it will change its behavior. So this is actually the microscopic behavior. This is the undeterministic nature of this electron, and we will discuss more about this indeterministic nature of this microphysical world in the next class. So in this class you can understand that what is the particle behavior and what is the wave behavior with respect to classical mechanics and with respect to quantum mechanics. So with respect to classical mechanics, but in the viewpoint of classical physics or in the viewpoint of macroscopic world, the particle and wave are mutually exclusive thing. But in quantum mechanics, this particle can behave like wave. Okay, so the electron can behave like wave. We have seen in the experiment, Davison-Garmer experiment also, and if you perform this kinds of experiment, so you can understand that here also the electron behaving like a wave, but in quantum mechanics, in quantum view, in microscopic view. But the most interesting thing is that you cannot predict its nature, you cannot determine its state at that time. So this is the undeterministic nature of this microphysical world. We will see this thing in detail in the next class. Okay, so for today